videos for WJC Maths M3 Pure M2.3.7a4, the reverse chain rule. So reversing the chain rule is frequently called integration by recognition. And you remember the chain rule from your previous set of videos, the differential videos. And it's a useful method for differentiating more complex functions, such as a function x raised to some power, or indeed a trigonometric function raised to a power, such as the examples I've given you there. So if we remember that the differential of a function, that's the notation I've used here is f of, where f is a function in x and g is a function in x, always comes out as being the differential of one function multiplied times the other one. So it's worth inspecting an integration that's the product of two functions to see if one is the differential of the other, or a multiple of the differential of the other, as the case may be. But I'll work up to that later on. So it's worth remembering, and it's a frequent mistake. People try to distribute or spread integration over multiplication. It doesn't work. Integration does not distribute over multiplication or division, and the way you get round that one I'll deal with later on in this series. So the integral of fx multiplied by g of x with respect to x is not equal to the integral of fx with respect to x multiplied by the g of x with respect to x integral thereof. So don't go there. So if I'm looking at something like the integral of 6x bracket x squared minus 1 all squared with respect to x, now I know I can expand this one out, but of course I will end up with a quartic, or a quadratic quartic if you like. There will be three terms in the expansion of x squared minus 1 with respect to x. And then I'd have to multiply out by 6x, so I'm going to end up with a quintic equation in three terms, and then I've got to integrate each term separately. So I can do it that way, but I'd really want a much faster method. The idea, a good mathematician is somebody who can choose the right approaches. So if I consider what I'd have to differentiate to end up with something like that, and the easiest thing to do is to identify the fact that the x squared minus 1, if I differentiate it, I'll get something of the form of the bit outside the bracket. So therefore, if I apply a really simplified integration rule, that's raise the power by 1. So if I take the x squared minus 1 and raise it to the power 3, 1 more than 2 that is, then its differential by the chain rule would be 3 times x squared minus 1 to the power 2 times 2x. Remember, you've got to differentiate the inside as well. As I said several times so far in this series, Dodi, differentiate the outside, differentiate the inside. Don't forget to differentiate the inside bit. So that would give me 6x bracket x squared minus 1 all squared, which just happens to be the thing I'm integrating. So a really simple step there, rather than having to expand it, getting a quintic, which I've then got to play with, is to say, all right, seeing as the differential of x squared minus 1 to the power 3 is what I want, what I'm trying to integrate, therefore the integral of it will be x squared minus 1 to the power 3 plus a constant. And it's much simpler to do that. Obviously, if I expand that cubic, I will get 4 terms, which fits with the fact that my quintic in 3 terms, when I integrate it, I'll get a sextic, a power 6 term, and I'll get 4 terms from this because, of course, the last term is a constant. It will be a minus 1, but minus 1 plus a constant is a constant, so therefore, it's working fine. Now, some further cases. These are ones where you'd have to jiggle around a little bit. So, as I've said already in words, it's worth deciding which is the root function, which is the bit that you're going to differentiate to arrive at the thing that you've got. And this takes practice, frequently called integration by recognition. So rather than having to integrate it step by step, you can do it by simplifying it, increase the power by 1 if it is a power, and then differentiate the result and inspect it to see what you've got. You might have to adjust the coefficient to make it behave itself, and you'll do that by either multiplication or division, frequently division, but not always. So if I'm looking at this particular integral here, no limits again, so I've got to remember my constant. The integral of 6x squared plus 4 bracket x cubed plus 2x all to the power 3 with respect to x. Now it's fairly obvious that if I differentiate the inside of the cubic bracket, then I'm going to end up with something of the same sort of format. The differential of x cubed plus 2x, of course, is 3x squared plus 2. And you can see that that is of the right sort of pattern to be the first bracket. So if I apply my simplified rule, I'm going to say, all right, I'm just going to increase that power 3 to become a power 4. X cubed plus 2x to the power 4, which I really don't want to expand because I get 5 terms and then I'd have a lot to deal with. If I differentiate it, again, here comes my chain rule. 4 multiplied, ignore the fact it's got anything inside it. So bracket to the power 4 will give me 4 bracket to the power 3. I'll then stick the x cubed plus 2x back in if you like, and then I've got to multiply by the differential of the inside, and the differential of x cubed plus 2x is 3x squared plus 2, as I've already said. So now I've got a factor 4 there, but that's identical to writing 2 times x cubed plus 2x to the power 3, and taking the factor, splitting my factor of 4 into 2 and 2, 2 times my 3x squared plus 2 will give me the 6x squared plus 4 that I need. So if I were to differentiate x cubed plus 2x all to the power 4, I would get 2 times the integral I'm looking for. So therefore, seeing as I haven't got that factor 2 there, what it is a half of that result. So therefore, it leads me to the situation where the integral of this is going to be 1/2 of x cubed plus 2x to the 4 plus a constant, because there are no limits there. Trigonometric one. Now remembering that the notation sine 4x is actually the sine of x all to the power 4, then, and we don't write it in that notation just so that we don't get confused with the sine of x raised to the power 4. So that's the standard notation for powers of trigonometry. So I can, in this case, it's fairly obvious that the thing that's got the power is the sine, and the differential of sine, of course, is cos, which makes life nice for me because it fits the pattern. So therefore, if I apply my simplified rule again, I'm looking at something of the form sine to the 5x. Apply my chain rule. 5 multiply by the power, bring the power by 1, down by 1, Wallace's rule. So I'll get 5 sine to the 4x, but then I've got to multiply by the differential of the inside. Remember, I could put brackets in here, but it makes it even more tedious than it is now. Differential of sine is cos, so therefore I'd end up with 5 sine 4x cos x. And that 5 is the multiplier that I haven't got. How do you get rid of a multiplication by 5? You do the inverse of multiplying by 5, which is either to divide by 5 or multiply by its inverse, which is 1/5. So therefore the integral, so this implies that the integral of what I've got is actually 1/5 of sine to the 5x plus a constant. If there were limits on this one, they would have to be in radians, but otherwise it works fine. This one, is not a log function because the top is not the differential at the bottom. It's the right sort of thing, and it's looking to trap you into that, but it's that power, extra power 2 on the bottom there. And I could do something as an alternative, but of course I know that I can treat that as the integral between my limits of 2x, x squared plus 1 to the power minus 2 with respect to x. And again, my root function in this case is fairly obviously the bracket with the power. So if I increase my power by 1, I would be looking at something of the form x squared plus 1 to the power minus 1. Use my chain rule to differentiate it, minus, because the differential of minus 1 is minus 1. Or multiply by the power, bring the power down by 1, behave yourself. So minus bracket x squared plus 1 all to the power minus 2, differentially inside 2x. So therefore that's the same as writing, of course, minus 2x over x squared plus 1 to the power 2. So you can see the only difference between what I've got is I'm trying to integrate, and what I would differentiate, if I differentiated x squared plus 1 to the power minus 1, is that negative sign there. So therefore it follows, therefore, the integral of 2x over that function in x with respect to x is minus x squared plus 1 to the power minus 1. I could treat that as 1 over x squared plus 1, or minus 1 over x squared plus 1 if I wanted to. It doesn't make any difference between my limits 2 and 0. Just suited my notation to use there. Obviously putting my upper limit in, 2 squared is 4, so I get minus 4 plus 1 to the power minus 1, minus minus, and watch that double negative coming in, 0 plus 1 to the power minus 1. Now minus 5 to the minus 1 is minus 1/5, and then I've got that minus minus, so I've got minus 1/5 plus 1, 4/5 is my final answer.